Perhaps in your perusing of maker sites and projects, you've come across the terms SPI or I2C or serial data before. Well, at the start of this chapter, I said that we'd be looking at serial data. But you may be thinking, didn't we already cover this when we looked at the serial monitor? And it's a valid question. The term serial data can be a little ambiguous in the sense that it can refer to any form of data that is sent as sequential bits in series along a data line. In previous chapters, we've looked at sending and receiving information via the UART port, which we can view with the Arduino serial monitor terminal. UART stands for Universal Asynchronous Receiver Transmitter and is used for communication to serial terminals and inter-device communication. It's great and all, but it does have its limitations. Now, for most sensors and devices, another common form of serial communication is better suited. In this section, we'll be looking at using the SPI interface with Arduino. SPI stands for Serial Peripheral Interface and is ideal for easy-to-use, high-speed communication between one or more devices. It's a synchronous form of communication, which means that it uses a clock signal to regulate the transfer of data. SPI is also a full duplex communication protocol, which means that data can be sent and received simultaneously, but it only supports a single master device. SPI requires 4 hardware lines to achieve this communication: the clock, the master in slave out, which is also known as MISO, the master out slave in, which is also known as MOSI, and a slave select line. A disadvantage of SPI is that it requires a slave select line for every slave device connected to the bus, as SPI doesn't use addresses such as with I2C. Instead, it uses the slave select line to notify a device of incoming data. The master device generates the clock when a device is engaged to receive data using the slave select line, and data is sent received in sync with the clock pulses. There are 4 different modes which SPI can operate in, and to determine the polarity and phase of the clock signal. And I've included a diagram in the section resources of the SPI transfer procedure and SPI mode selection. But here are the main steps. First, the slave select line is driven low, and this indicates to the slave that a transmission is incoming. The clock toggles on, and the master generates a square clock wave to the slave. The master and slave each sample read the first bit when the clock rises the first time, unless you are using falling logic, of course. And then as the clock falls, they each prepare for the next bit. Steps 3 and 4 are repeated until all the data has been transferred or received. When data transfer is complete, slave select is set back to high by the master, which completes the transfer. So now that we know a bit about SPI, let's take a look at using it with an Arduino. Bear in mind that whilst libraries exist to emulate the hardware functionality of the SPI port, these take up significant software overheads and resources. So if you're using a different Arduino board other than the Arduino Uno I'm using, then you'll need to ensure that it has a hardware SPI port. For the example, I'll be using shift registers we've already used previously, except this time rather than using the shift out function native to Arduino, we'll be transferring the data using SPI as a lower level function. This is much more efficient, and we're bypassing any extra software functions which might take up resources. I provided a wiring diagram in the section resources if you wish to copy this example. However, the exact same concept will work with any SPI device. Now let's take a look at the Arduino code that makes the magic all happen. So I'm in the Arduino IDE here, and you can see that the sketch is quite simple. As per our discussion on libraries, I've used include to include the SPI library, which is built in. You can find it by going to Sketch, Include Library, and selecting SPI, or SPI. Then I've got two variables here. I'm declaring slave select, which is the pin that we're going to use. Now Arduino has built-in pins for the hardware SPI port for the clock, MISO, and MOSI, and also the slave select if you're using it as a slave device. And these are through pin 13, 12, 11, and 10. However, slave select is just a standard digital pin that toggles up, high and low whenever it wishes for a transfer to happen, so you can use any digital pin you like. SPI automatically sets the pins for the hardware SPI port, so we don't have to worry about declaring those, just the slave select pin. So I've chosen pin 2. Then we've got delay time, which is going to control the speed, where I've got a binary counter rigged up here, so we'll control the sequential speed of that binary counter from 0 to 255, so an 8-bit counter. Then just some pin mode, setting slave select as an output. Then SPI.begin initializes the port. Then SPI.set bit order says that we wish to send the least significant bit of the data first. We can also change it to be the most significant bit, whichever way you like, or whatever the protocol of the slave device that you're using is. It doesn't really matter too much with the shift register, it's just going to change the order of the LEDs. Then there's a simple loop here, which creates a variable called I, a for loop, and it's going to run while ever I is less than 256. And each time it runs, it's going to increment I by 1, which gives us a incrementing decimal number, which when we convert it to or write it to the binary format that we're using along SPI, it'll create an LED binary counter for us. So the protocol here is really simple. Slave select goes low, which tells the slave device that we wish to initiate a transfer. At the same time, the hardware SPI port with the library will begin the clock. Then SPI transfer, we're writing the data here, so we're writing I, and I is an integer, which we're only using as an 8-bit value here, so we'll write whatever that byte is. Then digital write, it's going to write slave select high, which says that the transfer has completed after it's transferred its data, and it releases the slave select line, which stops the clock. Then we're going to wait for delay time, which is going to control how fast our animation sequence or our counter will increment. So let's go ahead and give it an upload. Connect your Arduino to your computer. I've already got this uploaded, so ignore the fact that the program starts up automatically. So it'll go through and compile, upload, and you can see that that's done uploading. So now that it's running on our board, you can see the binary counter, it's incrementing. You can see that fairly well. So it's happening quite quickly, and you'll notice that it shifts these LEDs up. Oh, that LED wasn't quite working. There we go. It shifts the LEDs sequentially along as each one before it fills up, which represents how the binary data works. So let's slow this down a little bit. Let's go to delay time and make it 250 milliseconds. So that'll compile and upload. Beautiful, so we can see our binary numbers being created. So the red light is blinking on and off to indicate every 1 and 0, every odd and even number. And so if we change least significant bit first to most significant bit, it's going to count from the other way, which is really cool. Some devices, however, require a specific order for the data, so don't rely on that rule carrying through. So when we upload it, you can see it beginning from that direction, which is pretty cool. And that's all there is to using the SPI hardware with Arduino. And it's really, really cool because you don't have to know about all of the intricate sending of the data. It takes care of all of it for you. The trick to remember is slave select line goes low, transfer your data, pull the slave select line back up, and you'll transfer that data along the SPI interface. So that's a bit about the SPI interface, and it's really, really cool because it's so easy to use. And in the next section, we're going to be taking a look at its closely related cousin, the I2C interface.